Hello dear students, into this another video of the size separation or the segregation. I am going to discuss the important method of it. It is known as the sieving. As in the previous video, that is introduction to the size separation, I have highlighted what is the sieve, what are the standards for the sieve, and so here the sieving method, into which this is the oldest method, into which we are using the number of sieves together to define the particle size of that particular powders and also to separate them. Basically, the passing of that particles through the sieve or the wire mesh, it depends upon the go or the no-go mechanisms. Means the particle diameters. Here I have shown the spherical particles, and this is the aperture side of the sieve opening. The diameter of the particles which are greater than the sieve opening, they are going to remain on the top, while the diameter of the particles which are equal to or generally less than the sieve opening, they are going to pass through that particular sieve opening and it will come out from the other side. So it depends upon the go or the no-go mechanism. Into this method, we are going to use the series of sieves. Generally, the sieves which is having the larger mesh, it indicates the lower sieve number, and as we are going from the top to the bottom, we are going for the finer mesh. So here we are using with the higher sieve number. So it is like that we are arranging the sieve in such a way the coarsest sieve is going to remain on the top, that it while the finest sieve is going to remain on the bottom. So the lower sieve number, the sieve with the lower sieve number is going to remain on the top, while the sieve with the higher sieve number is going to remain on the bottom. Here the sieves are therefore arranged in the increasing order from the top to the bottom, coarsest sieve and to the that is to the finest sieve, and the mixture to be separated, which is based on the coarsest sieve. It is on the top of the sieve, while at the bottom we are keeping a one fan to collect the water the particles which are passing through and that is coming out from the final sieve. Now this whole set of the sieves with the mixer to be separated is kept on the mechanical shaking machine to provide a different type of the movement, mechanical movement. Like some mechanical sieve shaker, they are going to provide only the shaking, some is providing the vibration, some is like a gyratory, that is circular motion, or some mechanical shakers are providing like a rotate movement, that's rotating and the tapping for the specified period of the time. Let's try to understand this working of this particular entire sieving methods by this particular video. In this video, this is the bottom pan that is going to be kept at the bottom, and then we are going to arrange the sieves as I have discussed earlier, into which we are going to keep with the sieve with the higher sieve number on the lower side, that is called as a finest sieve. And as we are going from the bottom to the up, okay, the sieve number is going to be decreased, so it means that slowly we are going from the top, and the top sieve will be the coarsest sieve on the top. So now, yeah, now as the sieves that are showing over here, that is going to be arranged as per the sieve number or as per their wire mesh size. And this is the lid which is going to keep on the top, because as the vibration is applying, so it will not dust, it will not produce the dusting. Now it is going to be fixed on that mechanical shaker, and after it is going to be fixed on the mechanical shaker, then the machine is going to be rotated at a specific speed for the specific period of the time. So now into this, all the sieves are going to be fixed into the mechanical shaker, and the electric supply is applied, and the powder mixer to be separated, it is kept on the top of the sieve, that is the coarsest sieve with the lower sieve number, and now again fixed. And see, the important part is that when we are keeping whatever the mixer we want to separate, powder mixer, we'll have to go for the definite weight. We are measuring the weight, and that definite weight of the mixer, powder mixer, we are generally keeping on the top of the sieve, that is the coarsest sieve with the lowest sieve number, and is going to be rotated for a particular period of the time at a particular speed, and then it is going to be stopped. So as you can see into this particular video, it is going to be rotated, and it is going to be second for a specific period of time at a specific frequency, and after a certain time period, the mechanical shaker is stopped, and we are just again carefully disassembling entire sieves and slowly taking out each of the sieve, starting from the top very carefully so there should not be any loss of powders. And the amount of the powder retained on the top of the each of the sieve is taken out and it is weighed. And later on, that amount of the powder which is retained on the each of the sieve, that is converted into the percentage retained and the cumulative percentage retained. As the amount of the sample which is retained on the each of the sieve is collected carefully and it is weighed. As for example, let's try to understand this particular thing. So the table is given. In the table, it is given the sieve number and the weight retained. Let's say the amount of the weight retained between the sieve number 10 to 16, it is the W1. That is the weight of the powder which is written in the sieve number 16 and which is represented as a W1, and which is going to be converted into the percentage that is written, that is given over here by the P1, and the cumulative percentage retained on the each of the sieve is calculated or find out by adding the previous one. So in this case the cumulative is going to be P1 only. If it is the next is 16 to 30, so weight is retained on the sieve number 22, it is W2. So percentage retained on the sieve, that is, let's say, the P2. So the cumulative percent retained is P1 plus P2. Similarly, we go from the other all the screen. So by finding this percentage retained and the cumulative percent retained as well as the weight retained, we can express the particle size distribution into the different curves to indicate the percentage of the particles lying in the particular size range. Basically, the sieving methods are of the two types. The first, that's called the dry sieving, and the another called as a wet sieving. Now, basically, the sieves are going to remain same. All the standards what I've given in my previous video of the size application introduction for the standards for the sieves, they are also going to remain same. So only in the case of into this slide, I'm just highlighting the what is the difference in the sieve which is going to be used for the separation of the dry mixture and which is going to be used for the separation of the wet mixture. You can see that the wire mesh is almost going to be remain same or what is the required one, but only the metal frame which is present, the size or the width of the metal frame is going to be increased in the case of wet sieving. The dry sieving is basically used to determine the particle size of the dry free flowing material, and it is basically suitable for if the particles are in the range of 1330 microns to 125 millimeter, while the weight sieving is basically used for the determination of the particle size distribution of the insoluble powders, insoluble solid particles in the liquid, and which are tend to stick together and will not able to separate using the just mechanical shaking, and it is generally used for the particle size from the 20 micron to the 3 millimeter. Now try to understand some of the advantages. As the sieving method is the oldest method, is easy to perform, relatively inexpensive, and it is suitable for the wider size range of the particles too. But some of the problems associated with this sieving techniques will be there, or the method will be there, that is the lack of reproducibility. It means it depends upon the orientation of the particles, which will depend whether the particles are going to be passed or it will not pass through the sieve opening. So when the particles are going to come into the contact with the sieve opening, what is the arrangement or what is the orientation of the particle, that will decide whether the particle will pass through the sieve opening or will not pass. The another disadvantage that's associated with that is the wear and damage may occur in the use of the cleaning, higher labor cost. Sometimes the particles are going to be agglomerate together because they are acquiring the electrostatic charges and which lead to the formation of the aggregates. And the particle size plays here the most important role because, as for example, let's say the particles are not spherical in nature. Spherical is the ideal shape what we require for any of the part of particle. But let's say particles are like a rod shape into which we find the diameter is less while the length is going to be more. So in the case of rod shape particle, if we are going for the measurement of the particle size distribution by the sieving method, we will generally find the overestimate of the undersized particle is also possible. So this is all about the sieving method for the particle size separation.